Right, so welcome to video number 2 about sequential Monte Carlo samplers, which I'm making because it turns out it's about 6 months since I made video number 1, so probably about time to follow up on that a little bit. So in the previous video, just a very quick recap, we talked about kind of context basically, and we described a situation where we've got something that's called the target distribution, which is a probability distribution, normally written as pi. And we want to generate samples from it, but it's non-standard. And it might be non-standard because it's Bayes' theorem, and we've got a non-conjugate prior or a nonlinear model in there, or something like that. So what we want to do is we want to generate samples from the target, pi, so we can use them to estimate stuff, like the mean and variance of a model's parameters, something along those lines. And what we do is we define something called a proposal. So a proposal distribution, which is usually written as a Q. And we're going to say that Q is easy to sample from. So let's say it's a Gaussian or something like that. And so we generate a load of samples, which I'm denoting with superscripts. So x1 to xn from Q. And then we use those to realize estimates relating to the target. And long story short, like I say, it's in the previous video, we do this by calculating what's called importance weights, where let's say the weight of sample xi is the ratio of our target distribution evaluated at xi, divided by q at xi. So, like I say, it's in the previous video, but basically these weights, these importance weights, act as like a correction term to make up for the fact that we're sampling from Q, even though we're really interested in stuff to do with pi. And then at the end of the previous video, we finished by drawing this picture, where the horizontal axis is x, and then we said, well, let's say that our target distribution looks a bit like this. I'll put a bump in there just to make sure it's clear that that's it's a bit unusual, basically, a bit difficult to sample from directly. And let's say that our proposal distribution is actually a bit too wide, which actually happens very often. So we'll call that a Q. Then what happens, what might happen in this case, is you generate some samples, might look like this, and the majority of them are kind of useless because the weights, the importance weights associated with them are very small, because pi of x is very small in these regions. And actually the only samples with significant weights in this particular case would be these two. So it can be quite wasteful because you can end up generating lots and lots of samples. In fact, very few of them contribute to your overall sort of Monte Carlo estimates. So this is actually, you could think of this as the first step really in a sequential Monte Carlo sampler, but it is just importance sampling at this stage. Okay, so what do we do if we think this happens? We have ways of measuring when we think that we have not enough samples have significant weights, which we get into later. But what is it that we can do once we realize this has happened? So the most common trick is to use something called resampling. And so in this video, we'll talk through what that is, basically. Okay, so we already have our existing set of samples. I can write here x1 to xn n. And basically, what we're going to do is pick a new load of samples, which I'm going to give a tilde, x1 to xn, superscripts. And we're going to do that by sampling with replacement from the existing lot that we've got. So sampling with replacement. So every single one of our new samples, x tilde, will have already been in our existing set of samples. So how are we going to do this? We're going to say that the probability that x tilde, let's say, basically just, I'm going to ignore the superscript, but it just means any one of these samples, is equal to xi. So the ith of our current set of samples is, well, it's proportional to the weight, the importance weight associated with xi. And actually, because these are probabilities, so we'll have to sum to 1, what we actually do is we define, if I go over here, so I'll probably use another tilde. This is equal to the weight associated with xi divided by summation of the weights over all of the samples. So just say this is normalized. So actually what we say is, and the probability that we're going to choose xi is actually equal to this normalized weight. So basically, if we go back to our example here, the samples with higher importance weights are more likely to survive into our new set of samples here. Okay, so how's this really going to work? Well, we're going to pick first one of our existing samples as a candidate to come through to be in our new set of samples. Then we're going to choose to accept or reject that candidate into the new set depending on its normalized importance weight. So it's a bit clearer if we ask ourselves, what is the probability that one of our new samples is going to be equal to, let's write a lowercase x. So a few things have to happen here. First of all, we have to pick our a sample from here. That sample then has to be equal to lowercase x, and then we have to bring it into the new set. So if I define capital I as a random variable which represents the index, so it takes values 1 to n, then we're going to say, well, for this to happen, then we're going to say that random variable I comes out as being lowercase I. So that means we've chosen the ith sample as our candidate. The next thing that has to happen is that our ith current sample is indeed equal to lowercase x. And then finally, we also have to accept that into our new set of samples. And so that is our normalized importance weight evaluated at lowercase x. So just worth reminding ourselves that this only works if lowercase x is one of these samples. So we're really restricted to the blue crosses. So if lowercase x is something else that isn't one of the blue crosses, then this probability will be 0. Okay, so we're sampling from these uniformly, sampling with replacement. So the probability that we choose the ith sample, that is change colour, hopefully. So this thing is really just equal to 1 over n. And just for the sake of simplicity, we'll say, okay, we know there's this normalized importance weight and it has this normalizing term. But this thing is just proportional to the weight evaluated at small x. And that is equal to, as we know, pi of x divided by q of x. So when you bear both of those things in mind, we end up with this probability being proportional to, so I'm now getting rid of the 1 over n basically, probability that the ith sample is equal to x multiplied by pi of x over q of x. So then the final thing that we're going to say is that if you have lots and lots of samples, so it's like an asymptotic argument going on here, we say as n tend towards infinity, then the probability that x, our ith sample, is equal to x should also tend towards the original proposal distribution, because I have more and more samples and they've all come from q of x. So as we get more samples, it should become more representative, if you like, of q of x. Roughly speaking, the histogram should look more and more like q. So as n gets really, really large, what we end up with is that the probability that one of our new samples is equal to x is proportional to pi of x, because setting this equal to q of x, it's going to cancel with this. So we end up losing, if we use our asymptotic argument here, then this becomes q of x, and then it cancels with this. So what we say at this point is, okay, well, if our samples, our new samples after resampling, are pretty much distributed according to the target, and then we can set all their weights equal to 0, because the weights were there to correct for the fact that we were originally sampling from Q. So we go on to say that the weights associated with all of our new samples, so x tilde I, they're all equal to 1. W and Q cancel out. Sorry, pi and Q cancel out, in other words. And that applies to all of our samples. Now, I'm being quite vague there because, well, we're saying that the new samples approximate our samples from pi, but they're kind of not, because we're restricted to only find replicas of these blue crosses, our original samples. So it might be an approximation of pi, but it only it's restricted to this grid, basically. And the other thing is, well, we're going to probably, if you look at these guys, they have low weights, low importance weights, so it's very improbable they will find their way into the new set. As these guys have relatively high weights, so it's probable that actually they'll get in several times. They can get in more than once because we're sampling with replacement. So what we will probably end up with here is, in our new set, is we'll have loads and loads of replicas of these, and we'll essentially delete these. So again, while we might have approximate samples from the target, we're only actually really now exploring these 2 points. And we think that perhaps we can do better than that. So what we've seen actually so far is iteration 1 of a sequential Monte Carlo sampler, and that is essentially just basic importance sampling, and that's what we've done so far. Well, now what we're going to do is we're going to, in the next video, look at iteration 2 and beyond. In iteration 2, what we're going to do is we're going to say, all right, we've deleted these in our resampling procedure. We've got repeated samples here. We know this region is important, so we're going to generate new samples kind of centered on these repeated blue crosses. And then we're going to use an importance framework again to try and improve our estimates associated with pi. So, like I say, in the next video, we break apart from standard importance sampling. We're into kind of iteration 2 of an SMC sampler.